이해가 되나요? 그 영어를 어느 정도 들으시는지를 잘 몰라서 그런데 제가 이거를 보면서 에니그마머신에 대해서 이거 보다가도 더 잘 설명할 수가 없어요. 작동 원리에 대해서는 거의 완벽하게 설명을 하고 있는데 저는 이거를 보고 아주 감동을 했습니다. 이 원리를 굉장히 잘 설명하고 있는데 우선 우리가 앞에서 고대 그리스 스파르타 때 사용했던 스키테일 암호 방법은 이제 글자를 몇 개씩 띄우기 때문에 이걸로 치면 예를 들어서 X라는 키보드를 치면 그 램프에 P가 들어오는데 그건 항상 동일한 P가 들어오는 겁니다. 그런데 여기서는 X키를 매번 치면 램프 불이 매번 달라요. 그러니까 이게 해독하기가 어려운 겁니다. 그런데 이제 그러면 독일에서는 어떻게 메시지를 전달했느냐 하면 아까 여기 이제 로타라고 했었는데 로타가 5개가 있습니다. 5개 중에서 1, 2, 3, 4, 5번 중에서 어느 로타를 사용하는 건가? 그러니까 5개 중에서 3개를 선택을 하고 3개 중에서도 순서를 어떻게 할 거냐? 그거에 따라서 달라지는 거죠. 그런 다음에 제일 처음에 시작할 때 로타의 위치를 어디로 둘 거냐? 그거에 따라서 또 달라져요. 그래서 로타 선택하는 가지수가 60가지, 로타 세팅하는 게 로타 하나당 1번부터 26번까지이기 때문에 스타팅 포인트를 그 중에서 임의의 숫자로 시작할 수 있으니까 26 곱하기 26 곱하기 26에서 17,576가지. 그 다음에 플러그 보드라고 앞에 있었는데 다시 한번 A를 G, G를 K 이렇게 바꿔주는 게 있습니다. 그래서 이거는 26개 중에서 20개를 선정해서 표를 묶는 거기 때문에 26개에서 20개를 선택하는 가지수에다가 그 다음에 이제 20개이기 때문에 19에서 1 해서 요거만 해도 150조 가지수가 돼. 그래서 이거를 다 곱해보면 요거 하나에 대해서 요만큼, 요거 한 가지에 대해서 이만큼 가지수가 있기 때문에 전체 가지수는, 전체 경우의 수는 이 전체를 다 곱해줘야 돼요. 그러면 최종 결과가 1해 5818경, 그러니까 천문학적인 숫자죠. 그러니까 이거를 일일이 하나하나 해보면서 맞는 걸 찾을 수가 없습니다. 그러니까 그래서 요게 당시에 실제로 사용했던 독일에서 사용했던 암호표입니다. 요거는 1940년 11월에 사용했던 건데 11월 요게 이제 1일, 2일, 3일, 4일 해서 매일 이거를 다르게 쓰는 겁니다. 그래서 1일 같으면 로타를 1, 3, 5 이런 순서로 하고 그 다음에 총이 시작 번호를 22, 21, 02 이렇게 하고 그 다음에 앞에 그 플러그 보드에 숫자를 A하고 D를 연결하고 B하고 H를 연결하고 이렇게 하라는 겁니다. 그렇게 해서 그래서 요거를 보내는 척하고 받는 척해서 기계를 똑같이 세팅을 해 놓으면 동일한 결과를 얻을 수가 있어요. 그래서 이제 메시지를 주고받을 수 있는데 그러니까 연합구청에서 이거 한 장만 가지고 있으면 해독이 되는 겁니다. 그런데 이거를 구할 수가 없는 거죠. 그래서 이게 만약에 배가 침몰해서 이것이 종이로 인쇄했는데 떠다닌다. 그러면 연합구청에서 이거를 구할 수 있을 거 아니에요. 그래서 독일에서는 이게 물에 들어가면 그냥 글자가 다 뭉개지게 그렇게 했다고 그래요. 그러니까 2차 대전 당시에 초기에는 에니그마머신을 쓴다는 거는 알았는데 해독할 방법이 없는 거예요. 그래서 처음에는 어려움을 겪었는데 에니그마머신도 이제 문제점이 좀 있었어요. 이게 어떤 거냐 하면 아까 X라는 키를 치면 매번 칠 때마다 다른 것들이 나오는데 다른 램프 불이 들어오는데 X 키를 치면 절대로 X 키는 안 나온다는 거죠. 그거를 연합군청에서 알은 겁니다. 그리고 좀 이따가 다시 뒤에 여기서 나오겠지만 이제 독일에서 매일 아침에 그날 수행할 작전 지시를 내려주는데 이게 다 이제 모르스 부호를 띠띠띠 하는 그걸 하는 거예요. 이때만 해도 디지털 컴퓨터가 없던 시절입니다. 그렇게 해서 전송을 하는데 아침에 항상 뭐 하이 히틀러 뭐 이런 거라든지 오늘 날씨 이런 거를 먼저 얘기를 했다고 그래요. 그리고 그게 동일한 메시지인데 매번 다르게 나오는 거니까 거기서 힌트를 얻어가지고 이거를 해독을 하게 된 겁니다. 연합구청에서. 그래서 두 번째 영상도 다시 한번 보죠.
This is such an inspiring story because it
로터입니다.
shows how mathematicians can save lives. We're talking about one of the most famous cipher machines of all time. It's a code machine called the Enigma
닥터입니다.
machine, used by Nazi Germany in World War II to send secret coded messages. And we've got one over here.
영국 사람이라 발음이 영국식입니다.
This is an original Enigma machine actually used
실제
in
기계입니다.
World War II. This was made in 1936. It's an army Enigma machine. Let's see how it works. So this belongs to a man called Simon Singh. He's an author, he writes popular science books, and he lends it to the University of Cambridge, where I work. This was found in a French field, I was told, by an American cryptographer after the war, and he took it home. So I guess he took it home as this souvenir. Yoink, that's mine. The guy who found it died about 12 years ago, and when he died, that's when Simon Singh bought the machine. We're going to send a message. Now, we were talking about what to send before, so we send number file. Let's turn this into Enigma code. So I'm going to type in N to begin with. As you can see there, the letter Y lights up. So N becomes Y, your code lights up. Let's write that down. Let's do the next letter, U. U becomes T. Let's do M. And I've got H this time. B. And E is W. Notice here we had Y turn up twice, and they turned up for two different letters. So N became Y, then later on E became Y. That's unusual. The other unusual thing you may notice is that the two E's in number file have turned into two different letters. So here E became Y, but the second E became W. Now this is why the Germans thought they had an unbreakable code. Old-fashioned codes in the past, pen and paper codes that they used to use, if you had the same letter, it would become the same letter in the code. Enigma is different. Probably each time you did it, you would get a completely different code. Now, if we can break this code, and by we, I mean the Polish, the British, and the Americans, if we can break this code in World War II, we'll be able to read those German secret messages, which is what we did. So let me show you how this machine works. Let me open up the machine. So we have three things here at the top. These things are called rotors, and inside those rotors, try and imagine lots of wiring, and it's all crisscrossed wiring as well. Now, if I press a letter, have a look what happens. The rotors move. When this rotor does a full turn, it will kick the next rotor one place, and then the right-hand rotor keeps going.
요게 한 바퀴 돌면 요게 하나 지나가고, 요게 한 바퀴 지나가면 또 요게 한 칸 넘어가고
그렇게. Fast rotor, a middle rotor, and a slow rotor. Imagine it like it's hands on a clock, like you've got a minute hand and an hour hand and a second hand. That's the idea. Brilliant machine though this is, all it is really is just a circuit. Here is a battery. You can see that's a modern battery in there. We've converted this. And this battery is connected to a bulb, and it lights up. It's the most simple thing you can make. A battery and a bulb, the bulb lights up, and that's all it is. The clever bit is the wires of the circuit are inside the rotors. So when the wires turn, the battery will connect to a different bulb. Let's try and see that happen. So I'm going to turn the wires, and the battery connects to this bulb. Do it again. I'm going to turn the wires, and the battery connects to this bulb. Changes. Do it again. Turn the wires, and the battery connects to this bulb. And that's why it changes each time, because it has moving parts inside. But otherwise, it's just a simple circuit. I think we need to know how to decode. This would be no good if we can't decode our message. So let's do that. Right. First of all, we're going to take our code here. We need to know what the setting was. Now, if you notice in the little windows, we have three numbers. It's like a combination lock, like a bike lock. Now, I took a note of what those three numbers were. Those three numbers, when we started writing number file, were 13, 9, and 21. So the idea is you would type in your message and you would get a code.
초기 값을 이렇게 세팅한다는 얘기죠.
Transmit, so you would have to write that code on a piece of paper. So that piece of paper would be given to the radio operator, who would then transmit the message by radio, by Morse code. That would travel miles away. So now imagine a second German officer, maybe on a ship somewhere in the ocean. Now he's tuning into that radio signal. He can hear the code, it's coming in, and he writes it down. Now this second officer will have an Enigma machine as well. And his Enigma machine is exactly the same as the first one. So there's something I have to do. I now need to set these rotors to the correct position. So we've got this code over here, Y, T, H, M, Y, and whatever. Let's type that into the machine this time and see what happens. Okay, so we start with Y. Y becomes
아까 넘버 P를 치면 이렇게 나왔는데 요게 이제 라디오파로 멀리 전송이 되는 거죠. 그럼 요거를 다시 치면 세팅을 똑같이 하고 요거를 치면 아까 했던 넘버 P이 나온다는 겁니다.
F and W finally is E. So each rotor has 26 starting places. In fact, these rotors come out and swap over. In fact, again, they had 5 rotors to pick from. They had a box of 5 rotors. You pick 3 from a box of 5. And already we've got thousands of settings, and each one will produce a different code. So we're going to work out those combinations. So the first thing I said was we pick 3 rotors from a box of 5. In the first slot, you would have 5 rotors to pick from. Once you've picked that, in the second place, you would have 4 rotors to pick from. And in the final place, the third place, you would have 3 rotors left. And you multiply those numbers together. So it's 5 times 4 times 3. So there are 60 ways that you can put in 3 rotors from a choice of 5. We have 26 starting positions for each rotor. So we have 26 choices for the first one, 26 choices for the second one, and 26 choices for the third one. And if you do that, you get 26 cubed, which is 17,576.
경우의 수, 가지 수를 지금 헤아리는 겁니다.
Because the military, the Army, Air Force, Navy, had something extra. The commercial machines, if you were a bank or a business, you could buy an Enigma machine to use yourself, to send your own secrets. But the military had an extra bit. They had this thing at the front of the machine. Now this is called a plug board. And what it is, it's like an old-fashioned telephone switchboard, like an old patch board. We have 10 of these wires. And each of these wires connect 2 letters into a pair. So in this case, you might see the letter Q is going to connect with the letter E. Now you make 10 of those pairs. 2 letters in a pair will swap over. So if Q is connected to E, then Q and E would swap over. That's an extra level of scrambling only available to the military. Now this had the most number of combinations. Now this calculation is going to be the hardest calculation, but we can do it. So there are 26 letters in the alphabet. How many ways to arrange 26 letters? Well, it's 26 times 25 times 24, all the way down to 1. That's 26 factorial, but we don't want every combination of 26 letters. We only want to make 10 pairs. That means there are 6 letters left over, which we don't care about. Because we don't care about them, that means we're allowed to divide. And we're going to divide by 6 factorial. Now there are 10 pairs. We don't care what order those 10 pairs are in. Because we don't care about it, we can divide by 10 factorial. And the last thing to divide by, 2 letters in a pair, well, if I swap them over, that would still be the same pair. If I had A and B, that's the same as B and A. That's still the same pair. So I can divide by 2. And I do that for each pair. There's 10 pairs. So I'm going to divide by 2 10 times, which is 2 to the power 10. And that is how many ways
내가
to connect
계산한 것보다 조금 다른 방식으로 계산하고 있는데 결과는 같습니다.
How big is that number? Shall we do that? 150 trillion, 738 billion, 274 million, 937,250. So the total 158 quintillion, 962 quadrillion, 555 trillion, 217 billion, 826,360,000 flat.
이만큼의 가지수가
That is
존재한다는
the total number of ways that you can set the Enigma machine. This would be an army Enigma machine around about 1939.
You were telling me that the Germans would send each other messages like number file or
Yes, they did that all the time. Yeah.
or send the U-boat to this position or whatever. But how were they telling each other their plug settings and their starting rotor numbers?
So this is very important. So these two people who are miles apart need to have the same setting. Now the setting was written down for you on a piece of paper. What they'd have is a sheet of paper like that, and it would be a big sheet of paper for each day of the month. So it was a monthly sheet. For each day of the month it told you how to set the machine for that day. If you didn't have this sheet of paper, you wouldn't know what the setting was that you had to use for that day. A nice little story, the Navy would write these code books in soluble ink. So if you get sunk, if you get caught, if you throw the code book into water, that's how you keep the secret.
It sounds to me that all you need is an Enigma machine and a copy of that book, and you know everything they're saying.
You would do. So if you had the machine and you had that code sheet, you would be able to decode all the messages. Fantastic, great. But we had the machine, and once we've had the machine, we can pull it apart and find out how it works. Great. But it was getting those code sheets. That was difficult. They were monthly, they would change every month. If you did capture them, which we did occasionally, you could use it until it runs out. But without a code sheet, you would have to break the code, and you would have to do that with mathematics.
What was the key? What was wrong with Enigma? What was its weakness?
Let's have a look at what the flaw is in the Enigma machine. So the Germans thought it was unbreakable, but there is a flaw. If I press a letter K,
그래서 이게 지금 여기서 얘기하고 있는 게 뭐냐면 독일에서 그 매월 요거를 하나씩 만들어서 보낸다는 겁니다. 그러니까 예를 들어서 2개월 뒤에 요 코드 시트를 미리 만들어서 보내는 게 아니고 매월 월초 또는 뭐 월말에 이거를 하나씩 만들어서 모든 부대에 뿌리는 겁니다. 그러니까 나치의 이제 히틀러가 요거를 매월 하나씩 만들어 가지고 전 군에 뿌린다는 거죠. 그래서 이거를 구할 수가 없다는 겁니다. 이거를 구하지 않으면 아까도 봤지만 뭐 1해 뭐 몇천 경 이런 가지수가 많기 때문에 그거를 다 해볼 수가 없어요. 그 가지수를 다 해보면 이제 말이 되는 뭐 우리가 보통 독일어로 이렇게 문장이 되는 그런 게 하나는 나올 텐데 그 가지수를 다 해보면 그거를 다 하기 전에 그냥 그거 다 해보려고 그러면 1년도 더 걸릴 겁니다. 그런데 매일 이게 바뀌니까 불가능하다는 거예요. 그래서 독일에서는 이거는 절대로 해독할 수 없어 이렇게 믿었다는 거죠. 그런데 여기에도 이제 허점이 있는 거를 알게 됩니다. 그래서 여러분들 그 The Imitation Game이라는 영화를 보면 바로 이 얘기가 나오거든요. 거기서 그 앨런 튜어링이라고 이 사람이 범버 머신이라는 거를 만들어요. 그래서 이제 처음에는 계속 실패하는데 이제 이거를 해독하는 겁니다. 주의할 거는 이 당시는 아직 디지털 컴퓨터 나오기 전이야. 그런데 에니그마머신은 이게 디지털 머신입니다. 그러니까 디지털이라는 것이 나오기 전에 독일에서 디지털 머신을 만든 거예요. 그래서 그 앨런 튜어링이 결국은 여러분 시행 끝에 결국은 아침에 그 나치가 방송하면 방송 그때부터 열심히 돌려서 5분인가 10분 뒤에 해독을 해요. 오늘의 요 암호 해독 코드는 뭐다? 그거를 해독을 해서 그러면 이제 나치가 뭐 유보트 어디에는 오늘 어디로 공격하라 이런 게 다 있을 거 아닙니까? 그런데 이 영화에서도 보면 나오지만 해독을 했는데도 해독을 못한 것 같이 그렇게 행동을 하고 이거를 이제 연합군 측에 해서 연합군이 한 번에 독일을 제압할 수 있도록 이제 그런 작전을 펴는 게 이 영화에 나옵니다. 실제 있었던 이유고요. 요게 그러면 이게 에니그마 플로 여기에 에니그마 머신의 약점은 뭐냐? 아까 되겠지만 키보드를 치면 그 매번 바뀌는데 같은 건 안 나온다는 거죠. X를 치면 X의 불이 절대로 안 들어와. 그거만 해도 가지수가 확 주는 거잖아요. 그리고 이제 그 나머지는 이제 그 연합군청에서 보니까 매일 아침에 동일한 독일어 방송이 나오는 거야. 동일한 메시지가 이제 날아가는데 그것이 매번 다르게 타이핑되는 거야. 메시지는 같은데 매번 다르게 날아가는 거야. 그래서 거기에서도 가지수를 확 줄일 수가 있는 겁니다. 그 얘기를 나머지 영상에서 한번 보겠습니다.
So, here's the Enigma machine again. Now, if I press the letter K, there we go, the letter Q lights up this time. Now, if I keep pressing the letter K, a different letter lights up each time. So a double letter would not be a double letter in the code. So it's a very good code indeed. But it is never K itself. So this was the flaw. A letter never becomes itself. So A is not A, B is not B, and so on. Z is not Z. This is a clue. So the way you break the Enigma code is if you imagine you have an Enigma message, you try and guess a word or a phrase that might appear in that message. Now, every morning, 6 o'clock in the morning, the Germans would send a weather report. Now, that was a standard form. That was always the same every day, apart from the actual weather. It was always a standard format. So we can pick a word that's going to be in that weather report. We might pick the word or phrase weather report, or Wetterbericht in German. And I apologise now if I've translated that badly. My Deutsch ist sehr schlecht. Entschuldigung. Now, I'm going to write Wetterbericht on a piece of paper. That's weather report.
weather report라는 뜻입니다. 독일어로.
I've got an Enigma code.
이게 매일 동일하게 weather report로 시작을 하는데
Underneath the code. Now I'm going to try and find where this phrase.
그 매일 아침에 보면 이제 이런 메시지가 나가는데 요거라는 거죠, 이게.
So it can't fit here because I have a T becoming T. So that's not where it fits. Let's try this. Can it fit here? No, I've got this T matching with T.
T는 절대로 T가 될 수 없는 이렇게 된다는 건 이게 아니라는 거지. 그러니까 경우의 수가 확 줄어드는 겁니다.
No matching. From what I can see, no matching letters there, so it might fit there. If I try that, see, look, those R's match up, so it can't.
이 경우도 아니다.
So maybe it's here. Maybe this is the phrase weather report. Now, from this point, we can start breaking the Enigma code. So you could use different phrases. Try and imagine what a German officer would send in World War II. So, for example, messages would end with Heil Hitler. So is it Heil Hitler at the end of the message? Now, if it is, we shouldn't have any letters matching with Heil Hitler. H's, E's, I's, and L. What the British codebreaker Alan Turing had to do was find a way to use this flaw to break Enigma messages. So he built a huge machine called the bomb machine. It was designed by Alan Turing and another codebreaker called Gordon Welshman. It was a big machine, noisy thing, it would rattle around, and this could help you break the code in under 20 minutes. So you would have to break the code every morning. So every morning the settings for the Enigma machine would change. So all the Enigma machines would change, stroke of midnight. So that's why a machine that could break the code that quickly was so important. So the bomb machine tried to work out the plug board at the front of the Enigma machine. If we go back, at the front of the Enigma machine, we have this thing called the plug board that connects letters into pairs. You actually make 10 pairs of letters. When I press a letter, the signal first goes through the plug board. It then goes through the first rotor, through the second rotor, through the third rotor, it then loops back, then it goes through the machine again in reverse order. So then it goes through the third rotor, the second rotor, the first rotor, and finally it goes through the plug board one more time and it lights up one of these bulbs. Now I'm going to try and draw that for you, but I'm going to make it as simple as I can. Let's try and do that. So, first of all, it goes through the plug board, then it goes through all the rotors, and I'm going to call that just one big magic box called R for rotors. And the last thing it does is it goes through the plug board. If we look at our weather report here, let's look E. Let me do that. If I press T, it goes through the plug board, through all the rotors, through the plug board again, and out comes E. Now we're going to use this to work out the plug board. I'm going to make one guess. I'm going to guess T is connected to A on the plug board. That's a guess, but I'm going to use it. So let's say that means that T goes through the plug board and out comes A. Now A goes through the rotors. Now we know how the rotors are wired up. So we know that, we pick a position and find out what happens to A. That's not hard to do. And I don't know, let's make something up. Let's say it comes out as P. But if I do that, I can deduce that P goes through the plug board and becomes E, which means I can deduce that P is connected to E on the plug board. Now that's pretty cool. So you've worked out one of the plug board settings. If that
플러그 보드입니다.
P
발음이 좀 이상한데 플러그 보드.
So I've done this a few more times doing the same method.
플러그 보드, 로터 플러그 보드.
And I've discovered a few more plug board settings. So the first one we discovered was PE. Now I've discovered K and Q are connected on the plug board. I've discovered X and B are connected on the plug board. And I've discovered T and G are connected on the plug board. But this last one is a problem. I've discovered that T and G are connected on the plug board. But I guessed that T and A were connected on the plug board. And it can't be both. This is called a contradiction. It can't be both TA and TG at the same time. This means my guess, the TA, was wrong. Throw it away, I got it wrong. Now I'm going to check the next one. What, TB? I might check TC, TD. I have to do all 26 options. TA, TB, TC, TZ. If all the 26 options are wrong, that means your rotor position is wrong. And what you do is you go, click, you check the next rotor position, and you go through all that again. Now that would take a very long time. So Alan Turing came up with two ways to make this a bit quicker. The first one, a really clever idea. He noticed that once you found one mistake, like TA and TG, this means that all these other deductions are also wrong, and they don't need to be checked. So they're all fruit of a poison tree. They can all be rejected at the same time, and you don't need to check them again. So that really speeds it up. The other way to speed it up is you can do this instantaneously with electrical circuits. So that's what the bomb machine did. It applied electrical current to my assumption, TA. The electrical current flows through the machine. It flows through TG, which means wrong. But it would also flow through all these other deductions, which means I can find all my deductions, which are all wrong, and I can do it instantaneously with electrical circuits. And then it will go click and check the next. And it will go through all the rotor positions in about 20 minutes. So the main thing to remember is the bomb machine is built a little bit backwards. It's a process of elimination. And so what you're left with is what wasn't wrong. And you would actually check that by hand and see if it works. The bomb machine was named in honor of a Polish code-breaking machine called Bomba. Bomba was a completely different machine, worked on a completely different principle. It wasn't a huge machine, you could sit it on your desk if you wanted to, and it exploited a flaw in the German procedures. Now they could use Bomba, the Polish could use Bomba to break Army and Air Force Enigma codes, but they couldn't break naval Enigma codes. So what Alan Turing had to do was find a way to break Army, Air Force and Navy Enigma codes. And it had to be a bit more robust, so that if the Germans choose to change their procedures, that this method would still work. What the Navy was doing differently is the rotor starting positions were actually sent at the beginning of each message, but they were sent in another code entirely. So it was a completely different code just to send the rotor starting positions. So you need to work out how that worked as well before you could even start breaking the naval code.
Is there anything that the makers of the Enigma machine could have done to have avoided this problem? Was there some simple thing that the Enigma makers could have put into that device there and it would have not have been broken like this?
Well, hindsight is a fabulous thing. You wanted to make it so that a letter could become itself. That was the flaw. And so the British Saw Enigma, we said that's a good idea, we'll have that, they nicked the idea. We saw Enigma and we decided to make one of our own. We called it the type X machine, except we took out the flaw. So a letter could sometimes become itself. This made it a more secure machine. Now from what I've heard, the Germans tried to break our code, but they concluded that it was better than the Enigma machine, so they gave up trying. At least that's what I've heard. It's very difficult to